So we can take the derivative of parametric equations very similarly to how we do for polar equations. We're just going to take the derivative of both the y and the x equations independently in terms of t, and then divide them by each other to find dy dx. And we can do this as long as the curve is what we call smooth, which means that both derivative values aren't equal to 0 at the same parameter value, because that's kind of like an indeterminate form, right? What's happening there? And it just usually means that there's a cusp point on the graph there, so we don't like that as much. Now, the trickier part is finding second derivatives. So finding the second derivative, right, d squared y over dx squared, right? That's just the derivative in terms of x, right, of the first derivative. Now, we have to remember, though, that dy dx here, this is going to be in terms of t, right? It's going to be in terms of the parameter because our x and y equations are in terms of the parameter, and we took respect to them in terms of t. So we need to be careful about this. So we need to kind of separate that d dx, right? So d dx is telling us to take the respect with x. So this is going to actually turn into a chain rule. So this is going to be equal to the same thing as taking the derivative with respect to t of dy dx. And we're going to multiply that by dt dx. Right? Because now if we look at this, right, the dt's would cancel out and we would still have d over dx, so derivative in terms of x. But dt dx, we have, so that's the derivative of a t equation in terms of x. That would mean we'd have to solve the x equation to be t equals instead. Well, that's not always possible. So what we can do is kind of say, okay, well, this is the same as the derivative with respect to t of dy dx all over dx dt, right? Because dt over dx, right, if we flip that into the bottom, right, we just make it the reciprocal of the fraction in the denominator. So now we can find dx dt and easily divide by that. And this probably seems a little confusing, but I'm going to go through an example and you're going to see what I mean. It's really just chain rule. We really just have to take the chain rule into effect because of the derivative of the bottom and because our equation is not in terms of y and x's, it's in terms of t. So we just need to be careful about that. So we're going to go ahead and find first and second derivative for the parametric equations, x equaling 2 times the square root of t and y of t equaling 3t cubed minus 2t. So if we go ahead and find our first derivative, we're going to find, we've got x of t is t to the 1/2, right? Or no, it's 2t to the 1/2. And y of t is 3t cubed minus 2t. Okay. Okay, so we got dx dt, right, or x prime of t is going to equal 2 times 1/2 times t to the negative 1/2. So that's going to give us 1 over the square root of t here for our dx dt. And then dy dt is going to equal 9t squared minus 2. Nice easy power rule polynomial. So to find our first derivative, right, dy dx, we're just going to divide those. So we had dy was 9t squared minus 2 over our x derivative, so 1 over the square root of t. Now that seems a little messy, so let's go ahead and rationalize this. Let's multiply top and bottom by the square root of t. Let's get rid of that complex fraction. So dy dx is going to actually equal 9t to the 5/2 minus 2t to the 1/2, right? We'll just make it fraction exponents to make our next derivative a little easier. So there's our first derivative. And now if we want to go ahead and find our second derivative, right, dy squared dx, oops, put 2 in the wrong spot, d squared y over dx squared, right, that's going to equal the derivative in terms of t of dy dx. So we're going to have to take derivative with respect to t, and then we're going to divide that by dx dt. Right, so that way we're still kind of taking the derivative with respect to x of our first derivative. So let's see, our derivative with respect to t of the first derivative, right? Using our power rule, that's going to be 45 over 2 times t to the 3/2 minus the 2 and the 1/2 are going to cancel out. We got t to the negative 1/2 here. And then we're going to divide that by our dx dt equation, which was, let's just write it as t to the negative 1/2. Right, so that's just equal to, whoops, there's a typo there. That's not a t in the bottom, that's a 2. Whoops. We got 45 over 2, t to the 3/2 minus t to the negative 1/2. And instead of dividing it by t to the negative 1/2, let's bring up that negative exponent and make it a positive half. So that means our second derivative is going to be 45 over 2, t to the 5/2, and then minus 1. Those two t's to the negative 1/2 and positive 1/2 will cancel each other out. So there's our second derivative. So d squared y over dx squared. So you just got to remember when you're taking second derivative with parametric that you're going to take the derivative with respect to t of your first derivative and then divide it by your first